Thank you, Jerry. Thank you, Jerry, for giving me this opportunity to present to this esteemed colleagues and friends here within the XAFS Society and the area of XAFS. My talk today would be to use how do we use hard X-ray core shell spectroscopy studies for battery materials. So the work that I'm presenting today is done within the framework of the Earth Abundant Cathode Active Material Consortium that is led by Jason Croy at Argonne. The Department of Energy, the Vehicle Transportation Office, is quite interested in developing energy storage systems which are safe, which are cost-effective and reliable for transportation applications. So there has been a lot of work that has taken place in this area over the past couple of decades. But now there is a significant interest in prioritizing the use of earth-abundant elements so that new chemistries can be developed that can be used for battery applications. It's particularly important because of the need for cheaper batteries, as well as having a good supply chain of materials so that some of the geopolitical concerns that might be there for how these materials that are critical materials that are used in these batteries can be relieved. So the main work that is done at Argonne is based on these materials called as lithium and manganese-rich materials, which is the baseline system that has been studied for over 20 years. We believe that this class of materials still hold significant promise in developing earth-abundant cathode materials. So this work is done within this consortium, and there is many different national labs and universities that are involved. A total of about 60 people are working in this project. Within that, ORNL's contribution is in the area of advanced characterization effort within the consortium using spectroscopy methods, potentially and hopefully neutron methods, and gas evolution analysis. In today's talk, I'll be talking about two aspects of the work that we have carried out in the past couple of years. The first aspect is related to exploratory work in trying to develop a fully earth-abundant cathode material, which is based on things like manganese and iron, which are quite prevalent in the Earth's crust. So the idea is that if we can make materials out of these Earth crust abundant materials, we might be able to replace more expensive critical materials which contain nickel and cobalt. There is a clear need to get away from cobalt and perhaps also to reduce nickel. As you can see from this plot here, where we are plotting the cell-specific energy versus a metric called as the minimum rated state of charge, these materials, which are called as the lithium and manganese-rich materials, show promise when compared to materials which are currently in use, such as nickel-based materials 811 and 622 or lithium iron phosphate. So we believe that if this material can be developed well, it can compete with LFP technology. However, there are a lot of challenges with this material, and one of the specific challenges that we are trying to address is how can we control a so-called property called as the low state of charge area-specific impedance, and we show that we can do that using doping strategies. The other one the first one, so I'll first start off with this area, which is development of iron and manganese-rich materials. So the pristine material that we formed is a lithium-rich manganese and iron material. If you look at it with an SEM, both the iron and manganese are uniformly distributed, And the X-ray diffraction pattern can be well understood apart from a few lines which cannot be indexed. The rest of it can be well understood by the R3 bar M structure, which is expected for these sort of layered compounds. However, when these materials are studied from a local perspective using XAFS, what you find is that the ion XAFS is very similar to one of the N members, LiFeO2, which is a cubic material, while the manganese XAFS is more similar to that of the parent material Li2MnO3. So this suggests that, or this shows that on this length scale that XAFS is sensitive to, on a nanoscale region, these materials show nanoscale inhomogeneity with the excess lithium clustered around the manganese, just as the excess lithiums are present around the manganese in this layer as shown here. And the iron, the fact that the XAFS of iron is largely similar to LiFeO2, it also shows that we have something which looks more like a cubic LiFeO2-like structure around the iron in this material. So the crystalline material is essentially what is considered as a layered rock salt composite in this material, and is not a simple uniform solid solution of the N members. When this material is electrochemically cycled versus lithium metal or versus graphite in an electrochemical cell, you get a profile which looks like this. So during the first charge, the voltage goes up. This is typically expected to be because of a conventional oxidation of the transition metal. In this case, it has, one would expect it to be iron going from a 3-valent state to a 4-valent state. And as you enter, there is a very large plateau, which is a fingerprint of almost all lithium-rich material. This plateau is called as the activation plateau, where the material gets activated by a process. And exactly the charge compensation behavior in this thing is considered to involve oxidation and reduction reactions involving the ligand, oxygen in this case. How exactly this process takes place is still being studied deeply in the scientific community, and it's highly debated. And this material can then be discharged, which follows either this blue curve here, or if you reduce the range in which this material is charged and discharged, you can follow the red curve. So in order to understand this material does not cycle very well, and we are interested in understanding the charge compensation process and the structural changes during electrochemical cycling. So we all know that typically X-ray absorption spectroscopy has been used to understand the oxidation state of the material. And we are interested in this case to understand how does the oxidation state of manganese and iron evolve during electrochemical cycling. It turns out that in the case of iron, as I have shown over here, for a variety of iron 3+ and iron 4+ compounds have a pre-edge which is more or less coincident, and it occurs at the same place. Furthermore, the edge shifts are small, and the edge shifts, particularly in this case, is not very systematic. For example, when you go to 4.3 volts, the edge is shifted a little bit more than that at 4.8 volts, and we expect higher oxidation, or at least the edge remaining at the same place if the oxidation state does not change. However, we see that that is not the case. So understanding oxidation state based purely on X-ray absorption is a little bit challenging. However, we also know that particularly in the case of iron, that the X-ray emission is quite sensitive to the spin state of the ion. And one might be able to link the spin state with the oxidation state. And so we have tried to integrate X-ray absorption spectroscopy and X-ray emission spectroscopy to understand charge balance phenomena in this material. So just to give a quick overview, I just mentioned that X-ray emission has significant sensitivity to spin states in some cases. And in an X-ray emission experiment, you just take a 1s electron and you excite it to an unoccupied state above the Fermi level. This can be done either resonantly or non-resonantly. And after the absorption process takes place, the system relaxes back to the ground state by emitting various photons or losing energy through OJ processes and other methods. So one of the processes that takes place is called the K-beta emission, where the electron falls from a 3p level to fill the 1s core hole state, giving rise to the K-beta fluorescence. In an appropriate region, if this fluorescence can be analyzed with about 1 EV resolution, you can get a spectra which looks somewhat like this, where you have what is called as the K-beta 1,3 main line and K-beta prime satellite line. It turns out that due to the exchange interaction between the 3p hole state that is created during the X-ray emission process, along with the spins that are present in the 3D manifold. So it is the 3p 3D exchange interaction gives rise to the splitting, and it encodes the spin information regarding what is there in the D manifold as viewed very locally on the atom that is being photo-excited. So this process becomes very clear in the case of iron when you use resonant excitation. So just to go over exactly how such a process could take place, here we show a schematic assuming a purely ionic, assuming that the ground state is purely ionic, where you take an Fe3+, which is in a 3D5+ state, so that the D manifold has these 5 upspin electrons in a high spin configuration. Now one can take, let us say we take this photon excites an electron into this so-called intermediate state here. So the downspin from the 1s state can be put into the 3D manifold. And this, in the presence of this pumped electron into the state, you can have a relaxation process where a 3p electron fills back the 1s core hole that was created to give rise to this K-beta 1,3 emission. Alternatively, one can consider taking the upspin electron and putting it into the D manifold. However, if you do that, what happens in this case, because all the 5 electrons are spin up, filling the available D states, you cannot put a spin up electron into this state. And so this transition where you try to take this 1s spin up electron and putting it into the D manifold will not be allowed. So essentially in this case, the minority spin state, that is a state which the spin that you have pumped up is opposite to what exists here, which is through the K-beta 1,3 is active, while the majority spin state is inactive. So there is no K-beta prime feature. And this can be seen by changing the incident energy and looking at and monitoring the X-ray fluorescence, the X-ray emission that comes out. So we can see a good strong feature here for the pre-edge in the K-beta 1,3, but there is no feature around here. There is no sharp rising feature around here for the K-beta prime. On the other hand, if we do the same sort of thought experiment on this 3D4 configuration of iron 4+, because we now have an empty state that is available in the 3D manifold, one can populate that either with both a minority spin as well as the majority spin. So this gives rise to emission, which would have channels, both the K-beta 1,3 channel as well as the K-beta prime channel become available. And thus, both the minority and majority spin state as seen through these channels, K beta prime and K beta 1,3 become active. So far, most of the discussion that I have done is assuming that the ground state is purely ionic. However, in these systems, particularly for the Fe4+, the ground state is actually very covalent in nature. So one can represent the ground state as an using this alpha times D4 and beta times D5 with an L bar, where this L bar corresponds to a hole on the oxygen. Even under these circumstances, as you can see here, we can still faithfully detect D4 character using X-ray emission methods. So we believe that looking at this using resonant X-ray emission gives us a fingerprint for locating to see if there is any D4 character in the ground state. So, so this is again just another. I'm just reiterating this fact that we have clear sensitivity to D4 in the ground state using X-ray emission. I should also point out that there is an extra feature here at slightly higher energies. This feature is typically attributed to a non-local transition, which involves the ion 4p at the absorbing atom interacting with a further away metal. In this case, I've just shown it as an ion 3D coupled through this exchange coupling through this oxygen 2p. We will not, in this talk, we will not consider this interaction further, other than noting that this feature is present in most of the compounds that we have studied. So with this, let me pause for break, Jerry, if that is okay.
That's fine. People can put questions in chat. I'll start a question. A great introduction to everything, Molly. Really thank you for the care. What are other methods where you, okay, so to start with, that D4 state is transient because of the charge transfer. Is that right? The ligand charge transfer?
I mean, it need not necessarily be transient. It could be a state which completely exists. The question is, can you see the state, and what is it that you're measuring, right? So Moss-Boyer spectroscopy is often used to look for ion oxidation state. I think you are hinting towards that as you started your question. Am I correct, Jerry?
Yeah, I'm wondering about when you have covalency, obviously you start worrying about the ligand charge transfer effects.
Exactly. Yes. And the Moss-Boyer shifts are also, just like X-ray absorption or X-ray emission has dependency on covalencies. The Moss-Boyer spectra also has it. Furthermore, in Moss-Boyer, the main thing which gives rise to the chemical shift depends on how much of the 4s electrons, how much it penetrates into the nucleus, right? That's what gives rise to the hyperfine interaction. So the kind of interaction that is involved in Moss-Boyer is different than the kind of interaction, the fundamental interaction which gives rise to a spectra in X-ray absorption. And we believe that X-ray absorption is another method which can provide information beyond what can be seen purely by Moss-Boyer.
Got it. Understood. A second question. If you go back one slide, I apologize. Just want to make sure I understand what we're talking about here is HERF-D, high energy resolution fluorescence detection at the beta 1,3 or at the beta prime?
Yes.
Okay. You were mentioning resonant XES. So that's gonna, are you gonna do, well, I guess you'll show us if you're doing a more full mapping of parameters.
Yeah, we have not done it in this case.
Okay.
We have done it in other cases, but I'm not going to get to that because much of that is not published yet.
All right. I think you should continue. Great start.
Thank you. Okay, so again, I'm going to go back and just tell you that this is the system that I'm going to be talking about. And let us dive a little bit into the system. And I should point out that all these experiments were done at the photon in, photon out X-ray spectroscopy pipox beamline, which is currently run by Chris Pollack at CHES. The spectrometer that is used just as a regular Rowland circle-based spectrometer using these analyzer crystals. I should have put down what this analyzer crystal was, but I haven't done it. Sorry about it. And this is the picture of from the back side of their setup. They have a setup where you can do two color emissions. So you could potentially look at iron as well as manganese simultaneously in this non-dispersive, approximately, I would say like 0.7 to 1 meter sort of SBCAs. You can get of the order of 1 eV resolution with it. Beautiful setup. The setup is extremely stable. It's a rock. Wonderful work can be done there. So here is the pre-edges now. This is the pre-edge of LiFeO2, which is a standard for 3+, and that is the pre-edge for SrFeO3, a standard for 4+. And you can see that the pristine compound has this classic double peak structure, which is typically associated with the presence of normally assigned to T2G and EG-like orbitals, or T2G or EG orbitals in the D manifold. Also, there are features over here which come from those non-local interactions. However, if you look at the same thing using K beta prime, you can see that where there is this intensity going up for the 4+ is not there for both the lithium LiFeO2 as well as the pristine compound, consistent with the ion being in a D5 octahedral situation. It's also, we have also performed X-ray absorption simultaneously, and the bond distances that we get is all consistent with what should be expected for D5 ion 3+. Now, when you charge it to this 4.1 volt, where we expect a little bit of oxidation, we do see that there is an increase in this peak, and more importantly, an increase in intensity showing up over here. We believe that this is, as we have discussed, based on the fingerprinting method, this is signature for the formation of ion, what one can call as the formally ion 4+, and correspondingly, the ion-oxygen bond distance shrinks a little bit, which is also consistent with the formation of ion, which is the formation of ion 4+ and oxidation of ion. Now, as you go further to 4.3 volts, this intensity increases, and there is more increase in intensity here. So we believe that the D4 character is fully developed, and the ion-oxygen correlation distance comes down all the way to 1.91 angstrom. This is consistent based on 1 electron oxidation that is expected for this chemistry, and is consistent with Coulomb counting that one can do while performing the electrochemistry. Now, if we go to 4.8 volts at the end of activation, where we believe something else happens, we see that at 4.3 volts, which is this blue line now, this feature actually comes down in intensity, and it becomes somewhat comparable to what you see at 4.1 volts. This clearly shows that some of the ion 4+ character is lost. This could be unexpected, because you are actually oxidizing the material, removing lithium from the compound as you are charging. So one does not expect a reduction of ion, but this reduction of ion can also be seen in the K beta 1,3, where there is an increase in this pre-edge peak, which we believe is because there is some ion which is moving to tetrahedral sites, and ion 3+ in tetrahedral sites would would show an increased pre-edge intensity. Moreover, one can follow the distances that are there from the XAFS, and we believe that based on the measurements that we have done here using the K beta prime, the K beta 1,3, and the XAFS, that there is ion in the tetrahedral site. And more importantly, from the XAFS, when compared to the first 3 samples, the pristine 4.1 and 4.3 volts, there is a significant intensity here, which can be clearly fit to an ion metal distance corresponding to 3.36 angstroms. This distance is consistent with the migration of ion from an octahedral site to a tetrahedral site in this material. And this clearly, in conjunction with what we see from the X-ray absorption, shows that surprisingly but interestingly, the ion actually oxidizes, the oxidized ion reduces to Fe3 plus and migrates, a part of the ion migrates to tetrahedral sites. This, we believe, is because this material actually loses oxygen, and the loss of oxygen in the material is compensated partly by the reduction of transition metal. So while that is true, we have also looked at the manganese, and the manganese spectra are just consistent with what we see for pure Li2MnO3, and we believe that there is no change in oxidation state, or actually in this case even the coordination structure of manganese. This behavior of pure Li2MnO3 is not seen in most other lithium-rich materials which are based on manganese and nickel. And this tells us that this material, one of the failure mechanisms might be because of the way the material partitions, and the Li2MnO3 that is formed, unfortunately, is behaving like pure Li2MnO3, which we have shown in prior work, loses oxygen instead of creating any other oxygen activity which will be cyclable. So, and in order to understand this, we can look at it while discharged. And here we are looking at the sample at a fully discharged state at 2 volt. And clearly, although there was no electroactivity of manganese during the charge, during full discharge, when you bring it back to 2 volts, there is a large shift in the edge and a large change in the pre-edge, which is all clearly showing that the manganese reduces. Analysis of the XAFS shows that we need a minimum of 2 manganese-oxygen bond distances and 2 manganese-manganese or manganese transition metal distance, clearly showing that we are forming Jahn-Teller distorted manganese 3 plus, which again, because of the large distortions that is associated with manganese 3 plus, is not good for a cathode material which has to be repeatedly cycled. So on the other hand, when you discharge and look at the ion, what we find is that the ion that had already migrated to a tetrahedral site comes back to the octahedral site, and most of the ion is present as Fe3 plus now in the octahedral site. We see little or no evidence for the formation of Fe2 plus. This is again a very interesting observation because in literature, many ion materials are supposed, the performance is supposed to be compromised by the formation of Fe2 plus. We don't see that in this material, so we think that there is some scope by which we might be able to engineer a better material and utilize the ion 3 plus 4 plus couple, which occurs at a higher voltage and can give us higher energy density. That is something that we would be doing in future. So this is just to wrap things up in this thing, and just for our visual pleasure, I just want to show that the manganese 4 oxygen, as expected at 2 volts, there is a splitting of this ion oxygen bond distance, as well as a splitting of this manganese transition metal distance. Both of this are consistent with the presence of Jahn-Teller ion. If you look at 4.8 volts and 3.6 volts, the ion distance is now split. The presence of the split distance is again consistent with the ion occupying tetrahedral sites in addition to octahedral sites at these voltages. So now I'll go for break 2 because I think this is the sort of work that we did on the iron manganese system. And we believe that what we have learned from this will allow us to design, hopefully, a better system with better rechargeability.
Really, really nice work. I've got a couple questions. First, Masood, can you unmute and ask your question? Well, I'll ask his question. He was curious if you were... Oh, go ahead, please, please.
Oh, can you hear me?
Yes,
Okay.
Masood.
Yes, thanks for your explanation. I was wondering whether you're planning to perform some multiple calculations for the pre-edges of the iron samples.
Yeah, well, I mean, we are doing multiplet calculations in another study. In this study, we wanted to initially start off with something where we can do direct fingerprinting. So we chose a system which was of technologically important to us, as well as something in which we believe that we would be able to address this question directly just by looking at the experimental data. So that's what we have done here. But we are doing both multiplet calculations as well as calculation based on very advanced density functional theory as part of this program. So stay tuned as
Okay,
we
amazing.
start publishing on this.
Amazing. Thank you.
Yeah.
All right. Second question is from Yulia Pushkar.
Hello, Mali. Nice to see you.
Hey, Yulia, good to see you too.
Yeah,
Good to hear you at least.
yeah. I have several questions. So first of all, I have a question about your sample. So was it like cycled to a certain potential and then somehow preserved, or is it in situ measurements?
This was not in situ. When we tried it in situ, there was huge ion reduction, and we could not stabilize the samples.
I see.
It was happening in I would say minutes time scale in this ID beamline with which is very hard to do. In fact, we had done this earlier once at 20 ID long back, and we find the presence of electrolyte really causes a lot of damage in the sample.
Okay, so you mean X-ray damage?
X-ray damage, yes.
Yeah, so the second question, of course, you're using the spectrometer, which is kind of attached to the beamline. So we developed this iron K-beta spectrometer following the Jerry philosophy. So we have a K-beta spectrometer, which basically can be mounted at any beamline. And we even used it with the bending magnet. So it would be interesting to check, let's say, RXES sensitivity for batteries, etc. Yeah, because we published one battery paper for manganese. I'll send it to you. So my final question is about the RXES, but you kind of alluded to it, that you try to do DFT. So basically, we have one study on the batteries where we have a RXES plane. And we are we really desire to compute that RXES at a good level. Maybe you can give us a little bit more information than just simply, oh, we're doing advanced DFT.
Well, I mean, the topic of this area is very debated now, right? If you look at, I would say that particularly how does the charge compensation take place in these materials during activation is quite debated, because it is clear that the ligand has to participate. Now, whether the participation is by ligand hole formation, where the oxygen stays put on the lattice and you're just creating holes on the oxygen, or whether you are forming molecules or dimers or trimers of oxygen, which somehow stays in the sample and is electrochemically active, right? So that is a very big area of research. We are addressing it. With regards to theory of this stuff, I think I will be able to, offline, I'll be able to talk to you, Yulia. We are still working on it. We have a group, a couple of groups, one in Europe and one here, with whom we are trying to do stuff. We are not fully convinced we have got everything right, but we are on the right track. But I'll be glad to talk to you.
Yeah, if you achieve some promising results, we're also very interested. Thank you.
Yep.
I'll ask a last question real fast. Valence to core XCS is really sensitive to the change between octahedral and tetrahedral coordination. You guys had XCS sitting there. Did you happen to look at the valence to core?
We did not do valence to core in this. This particular study was done mostly using the HERV-T.
I understand. Okay.
We have done valence to core in in the last beam run. We did a few. In fact, we did resonant valence to core. I don't know if we learned anything. We have the data.
Okay, very good. You should continue, please.
Okay. All right. So I'm going to continue now with the third part of this talk after the two breaks, and I will now concentrate on this area of what I wanted to present, corresponding to doping strategies to control or modify the performance of lithium and manganese-rich baseline materials. Now, one of the main issues with these materials, among other challenges, one of the challenges that we need to fix is here we are plotting what is called as the power to energy ratio. And the materials can deliver a fair amount of energy, but the power to energy ratio, when it goes up, the performance drops down. So, and this is maybe partly associated with this phenomena, which is called as how the area-specific impedance increases as a function of state of charge or voltage. In this region, which is shown in blue here, is a region where where sites which are in the layered component of this material are active. And in this region, it is sites which are in the Li2MnO3-like regions, which are active. So it is an LiMn6 type sites, and these are the layered sites. It is clear that in the layered region, the area-specific impedance is consistent with what we would see for any conventional material. However, for the x is equal to 0 sample, this area-specific impedance shoots up, which suggests that this material will not be able to deliver energy at a high rate of extraction of energy in these sort of lower voltage sites. So the question we had is, we know that these, let me go to the next thing. So this is how it looks. You have this Li2MnO3 like domains, and you have these layered regions, right? This is a schematic of it. And what we wanted to see is there a way we can selectively dope the Li2MnO3 and see if it affects the performance or the behavior of this material? And one of the first things that we chose was tin, because we know that Li2SnO3 has a very similar structure to Li2MnO3, and both tin and manganese are 4-valent. So we believe that we should be able to do some doping of manganese sites in this material, and we use this as a guide to design this. And in fact, we were pleasantly surprised that this sort of thinking that we had was actually correct, because when we put a small amount of tin dopant of the order of 1 or 2%, there is a significant flattening and lowering of the ASI, the area-specific impedance. On the other hand, if the doping level goes up, we see that it again becomes bad. So there is some critical amount of small amount of doping that one can put into these materials and improve its low voltage performance, low voltage power performance. So in order to understand this, first we needed to, having come up with this idea, we wanted to show that we can actually understand the tin site selectivity in this material. And so we performed synchrotron XRD. This work was done by Subhadip Malik, who's a postdoc at Argonne. And one of the important takeaways that he found is that when you dope small amounts of tin, for the small amounts of tin, early amounts, the tin seems to substitute in the lattice. But when we start going to higher amounts of tin, particularly for this composition, tin Li2SnO3 starts precipitating out. So we want to try to maintain it at these low concentrations. And in the case of this composite material, which is this has both, which is a lithium-rich material, tin can be substituted fairly well. And what we notice is that the microstrain that is there increases quite rapidly for small tin dopings, and the microstrain falls down as the doping level increases. So there seems to be some sort of a correlation from the strain and the particle size that one can extract, or the grain size that one can extract, and the ASI behavior of these samples. We then followed this up with XAFS because we wanted to understand the site occupancy of tin. And we were able to show that the tin dopants occupies manganese sites in these materials. However, because the tin manganese distance is significantly increased compared to the corresponding manganese distance. So in pure LiMnO3, the manganese distance is around 2.85. In this case, the tin manganese distance goes to the about 2.93 or 2.94. So that's about a 0.1 angstrom increase in distance. Similarly, in these materials which are more complex, the bond distances increase from 2.89 to about 2.99. So this work, I should point out, was performed using Ching Ma's help at the DND CAT at 5 p.m. So we also followed this up at TEM, and what we find is consistent with the X-ray diffraction. In the starting materials, the grains are fairly large, but the grains, I don't know how clear it is to see, but the grains break down into much smaller regions in these samples. And then if you look at the EDS spectra, what you find is that tin seems to have a propensity to go to these regions, which we believe are these grain boundary regions. So adding tin to this material seems to go into the lattice, but I think that what happens is these small nano domains are trying to purify themselves. And as they try to purify themselves, they are pushing the tin out to the grain boundaries. This leads to a significant reduction in grain size. There is an increase in the amount of stacking floral densities. And we believe that the kinetics is improved because the grain size is increased and something magical happens by which even with these small amounts of dopants, we are able to modify key electrochemical property, such as the area specific impedance, which we ourselves were not, well, we were pleasantly surprised that we were able to alter this. We hope that this will give us a vehicle to start looking into other dopants and seeing how we can maximize performance out of these materials. So last but not the least, I should show that we also looked at it with NMR. Fulya Dogan, who's an NMR expert, looked at this at Argonne. And again, consistent with the XAFS studies, what we find is that in the doped composite material, there is some extra intensity that can be assigned to environments which look like Li2Mn 0.98, tin 0.0203. That is, again, tin occupying manganese type sites, and that the excess lithium that is there in this material is also clustered around the tin, which is what we see with X-ray absorption as well. So in summary, I would just want to say that we have used X-ray absorption methods very gainfully to address key questions related to research and development of earth-abundant cathode active materials. We hope that this will help us to develop high-performance materials which are cost-effective and very reliable in their performance for electric vehicle applications. So I would be amiss without acknowledging the fantastic team of people that I worked with. CY Kwok is a postdoc with me. He took primary responsibility for all the X-ray work and doing a lot of communication with all the team members. I should also thank Subhadev, who attended many of the X-ray absorption beam times, staying awake late into the night and doing all the measurements. And he was responsible for many of the sample preparation and electrochemistry. I would like to thank DOE for sponsoring these activities and all the beamlines and the support that we have gotten in getting these work out. So the first part of the work, the manganese ion, is already published in Chemistry of Materials. And the second part of the work just recently is in the proof stage. And there is a DOI for that. So it should come online soon. With that, I wind up and ready to take questions.
Very good. Federico, you have a question for Molly.
Yeah. Hi, Mali. Wow, this was beautiful. Thanks a lot for showing this.
Thank you.
Have you thought of looking at the lithium perspective? Maybe looking at lithium spectra using inelastic scattering, X-ray Raman, or some other direct probing of the lithium?
A lot of lithium that we do, right? It's a wonderful question, right? Because these are the active material, the active element is lithium. It is always great to look at it from a lithium viewpoint. It is quite hard to get a good lithium XRS spectra out of these materials. The penetration depth suffers a little bit, and we can get some lithium, particularly when you remove a lot of lithium out of the material. It is hard to get it. Additionally, in many of these materials, the lithium edge is where it tends to be fairly close to the other M edges. It is certainly very close to that of cobalt, in which I have tried to look for it in lithium cobalt oxide. We haven't successfully seen it. We can see lithium in other materials based on other battery materials, lithium oxygen materials, lithium and electrolytes. We have been very successful in doing that. I know that Christoph at ESRF is also doing such studies. So yeah, I agree, there is a scope to do lithium studies.
Yeah, no, great. Thank you. This will be wonderful. I'm looking forward to seeing, yeah, some lithium spectra, maybe even during cycling this material. That will be great. Thanks, Gerald.
Thank you.
All right, we have a question whether the dopant segregation towards the grain boundaries improves the material's electrochemical performance, or I mean, is it a feature or a bug that the tin is going to the grain boundaries?
I mean, we believe it's an important feature that we design. I mean, we feel proud that we were able to design it, right? We just say, oh, we wanted to modify the response here at for the low voltage sites. And we believe that we have done that by tin doping.
Okay, but is the tin at the grain boundaries electrochemically active, or is
No,
it just changing impedance like a short resistor, or what role is it playing microscopically?
I mean, by the impedance that we are measuring here is a cell level impedance. Essentially, we are improving the kinetics of lithium transfer, the lithium migration within the material. And essentially, the grain sizes have become such that the lithium is able to traverse from one grain to another without hitting bottlenecks within the grain.
Okay, so let's push that a step farther. So you have the tin at the grain boundaries, but maybe the bigger picture is just the fact that now the system is so nanotextured and that there is a lot of grain boundary for lithium percolation. I mean, is the effective surface that the lithium can intercalate through increased because of the extreme nanodomain formation?
It's not, I mean, the nanodomains that we talked about that we see in X-ray absorption is a completely different length scale than the grains that you're seeing in the TEM. They are much larger.
No, I understand that. I'm talking about lithium transport, same as you were. So I'm trying to figure out what role does the tin at the grain boundaries play? Is it just that it caused the grain boundaries to exist, that it drove the system to make smaller and smaller domains that you see in the TEM? Or is it active somehow electrochemically?
The tin by itself is not electrochemically active. You cannot, I mean, this is purposely we wanted to choose an element which is not electrochemically active.
Understood. Okay. So you were actually here engineering the essentially the domain size to try to get more ways for the lithium to get in and get out, or that was the outcome?
Something like that, Jerry. We want to create nano highways.
Got it. Nano highways. Okay.
Just use some term which makes no sense, but we want to create nano highways.
Now that you've done it once, do you have a recommended dopant for NMC 811 that'll make it perform even better?
Oh, people have done people put molybdenum dopant, right? And with X-ray absorption, we have shown that the molybdenum stays as 6+. It cannot be electroactive at those voltage ranges.
So your suspicion is it's the same idea.
It is in the grain boundaries. We are never able to see a metal correlation corresponding to molybdenum in the lattice.
Got it.
So in
Okay.
that case, we've been, in fact, we wrote a patent on this 15 years ago
Very
while
good.
I was at Argonne.
All right, we have a last question from Robert Gordon.
Hey, Robert.
You there, Robert? You're muted. No mic. Okay, I'll ask his question. He's asking whether there's been prior studies using silver to coat the lithium iron oxide material at the nanoscale, maybe functionally similar to what the tin is doing here.
Which element did he say? Silver?
Silver, yeah.
Not that I know of, Jerry. People put all sorts of elements.
Okay.
People do ALD coating so that you can get conformal coatings. That people do, I mean, people try, not that tin is very cheap, but people try to see if you can go with the cheapest element that is possible. So that, I mean, lot of the things in energy storage, unlike catalysis, is driven by cost because the amount of material that you need is in the ton scale rather than in the kilogram scale.
Okay, though fortunately it's 1% dopant here, but yes, I take your meaning.
Yeah, yeah. I mean,
All right.
silver is a good thing. I don't know if anybody has done it.
Okay, very good. With that, everyone, let's thank Molly, and I'll stop the recording and we can have a few more minutes for discussion.
Thank you all for listening.